Hi, everyone. My name is Jenna Syposs, and I had a 6-month internship with LPI working with Julie Stopar on identifying impact craters in the 13 Artemis III regions. But for the sake of time, I'm just going to be going over examples of 5 craters. So before I get into the sites, I would first like to acknowledge the data sets that I utilized for this study. So from left to right on the screen, I utilized Landis et al. Volatile stability shapefiles, Lee et al. M cubed and LAMP detections, Barker et al. Lola DEMs of 5 meters per pixel, and Lee et al. Hematite integrated band depth detections. And I definitely want to emphasize that this project would have not been possible without the work from these scientists. So I just wanted to provide the proper acknowledgement. So our first candidate crater is located in the region, de Gerlache-Coker Massif, where image A is a Lola DEM hillshade of the entire region. And there's an overlay of various data sets where the light blue represents Moon Mineralogy Mapper or M cube detections that I spatially mapped out the regions for, and it's outlined in blue. I additionally added hematite detections, which were generously provided by Schweili. And I've also included volatile stability shapefiles. And in this case, the translucent purple is sulfur. So the crater of interest is located within the orange box, where image B is just a close-up view of the crater. And you can see that the M cube detection region intersects the crater. Image C is an elevation contour map. And I generated this in ArcMap from Lola elevation data. And each contour shell is in 200-meter intervals. So the dark green represents higher elevations, the red represents lower elevations. And I wanted to include this to show the correlation between higher relative elevations and better illumination conditions. And this particular crater has around 10 days of consistent illumination per month, which is above the 6-day minimum highlighted by the Artemis III SDT report. And image D is a slope map that I generated from Lola terrain slope data. And I constrained the slope from 0 to 5 degrees in dark green, teal from 5 to 10 degrees, and cyan blue from 10 to 15 degrees. And the crater is within the 10-degree range, which is ideal for traversing and LTVs. So this particular crater, I took a horizontal and a vertical profile of all the craters in the study. We then exported the profile data, ran it through a code which determined the depth to diameter of all the craters. And in this case, we got a depth to diameter ratio of 0.145, which is lower than what's typical of craters of this diameter. There should be around 0.21. So that indicates that this crater is older and that more erosional processes were at play. So our next candidate crater is within Nobile Rim 1. And again, image A is a Lola DEM hillshade of the entire region. And you may notice that there are a variety of hematite detections within the walls of Nobile crater, represented by the red, orange, and green pixels. And you could see it better in image B. The crater intersects a couple hematite detections and is in close proximity to a sulfur stability zone. Image C displays the elevation, where you could see that this crater has an elevation of around 6,800 meters, which is like the highest elevation we've seen so far. And image D is again the slope map, and it's definitely within the dark green 0 to 5 degrees terrain slope range, which is ideal for traversing. And additionally, this crater has around 9 days of consistent illumination per month. So this particular crater has a depth to diameter ratio of about 0.0641, which is way lower than average when it should be 0.21. And this is likely attributed to the fact that it's on the rim of Nobile crater, so that more mass wasting and infilling processes have lowered the depth to diameter ratio, making it shallower. So our next crater of interest is located in Nobile Rim 2. You may notice in image A how there's a large cutoff crater towards the left of the image, and that large unnamed crater holds a permanently shadowed region. So the crater of interest exists on the rim of this large unnamed crater, but also exists on the rim of Nobile crater as well. So you could see the crater better in image B, where it intersects an M³ detection region, and it's in close proximity to the volatiles sulfur, water, ammonium bicarbonate, ammonium carbonate, and toluene. I'm just going to skip to image D. The crater has the best traverse range around the rim of this large unnamed crater, and it additionally has around 10 days of consistent illumination, which is ideal. So this particular crater has the lowest depth to diameter ratio we've seen so far. It's about 0.03, which should be about 0.15. So that indicates that this crater is shallow indeed, and it's likely attributes to the fact that it's on the rim of this large unnamed crater, but also on the rim of Nobile crater also, which likely attributed to mass wasting and infilling processes. So our next candidate crater is located in Peak near Shackleton. It's a little bit difficult to see in image A, so I'm just going to skip to image B. This crater is tiny, as you may have guessed. It's within the M³ detection region, and it's also within the sulfur stability zone in purple. In image C, the elevation is not as dynamic as in other regions, so the stable elevation range is ideal, along with the slope, which you could see the large dark green band, which is a slope of around 0 to 5 degrees maximum. And I think the only downside with this particular crater is that there's only around 6 days of consistent illumination per month around this crater. So a lot of consideration for the timeline of visiting this crater would be required. So this crater is 120 meters in diameter, which is tiny. But what's cool about it is as a depth diameter ratio of 0.14 when it should be 0.15. So that indicates that this crater is much younger, which would help with impact chronology studies. And additionally, it indicates that it hasn't had much influence from solar impact gardening processes. Oops. And so our final crater is within Faustini Rim A. You may see that this region has a lot of volatile stability zones. So that indicates that Faustini Rim A is a much colder region than the others. And you can see in image B how this crater intersects the M³ region, and that dark blue pixel inside the crater is a hematite detection. And additionally, it hosts a variety of stable volatiles. Again, the downside with this region is that there's only about 6 days of consistent illumination per month. So then again, a careful consideration would be required to travel to explore the timeline of this crater. So this crater is 2.7 kilometers in diameter, so it's much larger than the other ones we looked at. And despite how pretty the horizontal and vertical profiles look in this crater, it has a lower than average depth to diameter ratio. So that indicates that despite the fact that this crater is morphologically crisp, it's not exactly a young crater because the ejecta has been degraded. And Julie will go into more detail with her presentation on Faustini, so stay tuned for that. So just to sum it up, we introduced examples of 5 impact craters that satisfy the Artemis III SDT report. And really, despite which Artemis candidate region is chosen as the final site, the next step would be to find a landing zone that would factor in slope, illumination, elevation conditions that would support our friends, but also harbor scientific potential that would answer important geological, chemical, astrophysical questions that are highlighted by the science objectives in the Artemis III SDT report. So lastly, I would like to acknowledge NASA's Survey's ICE-50 team for funding this project. And yeah, I'll be around if you guys have any questions. So thank you.